All right, you can begin.
Good afternoon. I'm presenting on error analysis, floating points, approximation of number, loss of significance and error propagation, stability in numerical computation. Sorry, I didn't put everything there, but the short form is error analysis. And the two people involved, Toby Akinwande and Emeka Inendi. I hope I got that right. So Emeka is working, so I have the huge responsibility to continue. So let me go to the next slide. Okay, so just for notes, all attendees should be muted. Please post your questions in the chat box or signify by raising your hands. So, okay, brief introduction. Why, what is numerical analysis? It facilitates difficulties encountered in analytical solutions to mathematical problems. So you might be asking, why do we do an numerical analysis? We do it where we engage in numerical analysis to solve complex mathematical problems, problems in physics, chemistry, in all areas, subjects of life. We engage the use of numerical analysis. Then this is another, so under this, we are going to also talk about errors, relative error, absolute error. We're also going to talk about the analysis of errors due to computation that brings about analysis in numerical methods. So as I spoke about applications of numerical analysis, the first application is used in airflow patterns in respiratory tract. It's used in machine learning, the use of algorithms of Newton's method. That's one of the areas where we use numerical analysis. Other aspects of applications are car safety enhancements, airflow patterns in respiratory tract, on and offset projections of tumor cells, weather predictions, financial industry, spacecraft industry. Okay, then. So these are the things we should note. We are talking about floating point approximation of numbers, loss of significance and error propagation, stability in numerical computations. Then we'll talk about the question and answers. So we'll also talk about sources of errors, absolute and relative error, round-off and truncation errors, well-conditioned and ill-conditioned. That's where we talk about stability. Okay, next slide. So, okay, when we talk about the floating point approximation, floating point approximation of numbers, we are talking about is either the representation is either decimal normalized floating point form or simply floating points. Okay, so next slide. Okay, so these are like representations. The next slide shows representations on how the floating point is called. So you might be asking, why do we use floating points? Floating point shows, when you use floating points, it's mostly used in a computer program. So we all know that numbers are stored as binary, zeros and ones on the computer. So normally we use floating points to show a binary number in a memory. Okay, so that is like a, yeah, okay, sorry, okay, let me go to the next slide. Okay, so sources of errors in numerical computations, that blunders, we have modeling errors, data uncertainty, discrimination errors. Okay, loss of significance and error propagation. So you can say a formula that E is equals to X minus E X star. So I'm going to use examples to explain it further. So this is an example. The X is equals to X star over X. So this is, yeah. Okay, so this is a clear example of absolute and relative error. So to get the error, we already know the value for X as 3.14, that number, minus that X star value. You subtract it, then you get a decimal point in it. So to represent it back, you have to put the zeros in front, and that's the number at it. So this is the absolute. This is how to calculate the absolute error. You get the value. We both know what the values of x are in both. We get them, then we get the absolute value, and that's the absolute value. To get the relative value, these are the formulations. These are the equations you use, and you just stick it in the formula, and you get the relative error. So, okay, this is still the same. It's like an example, still like an example, similar to the former ones. You get your error by getting, your value of E, the value of the other E, you slot it in the formula and you get your value. You get your E value, the error, the absolute error and the relative error. Now we are talking about round off and truncation of error. So I'm going to explain it briefly. The error caused by replacing a number by its closest machine number is called round-off error, and it's also called correct rounding. So this is an example. We approximate the following decimal numbers to 3 digits by using rounding and chopping truncation rules. So these are the values already. And we all know how to round off from secondary school. This is how you get for the rounding, and this is how we get for the chopping. So, okay, loss of significance. In place of relative error, we often have the concept of signal digits that is closely related to relative error. So this is how, this is a formula for relative error. So let's look at the example, because an example will show us closely how it's done. We have x as 1, 3. The approximate number is x is 0.33, and it has 3 significant figures. You slot in the value, you get 0.5 times 10 raised by minus 3. Let's do for the second example, x is equal to 0.02138. You slot in your values for x and xa, you get the value 0.5 times 10 raised by minus 2. Then for the third example, you get your value for x at 0.02132. You slot your values, and that's the signal number that you get. Okay, so stability. The process of evaluating a continuous differentiable f at a point x is equal to c. That's when you say a number is stable or is well conditioned, sorry. So let's use an example to explain it further. We have our fx as root x, and we have the conditions. The conditions is 0 and infinity sign. So we slot in the values. That's what we get. Then the condition of f is written, you get those values. Then at the end of the computation, you notice that f of xa is more closer to 0 than er is closer to e of r xa. So then this is another example, 10 all over 1 minus x cubed. So we know our f of x as 20, that's prime. When you differentiate, that is 20x 1 minus x squared. So we slot in the values. You know the f prime was that, and you know the f of x is that. So you slot in the values, you get the absolute value, and that's what you get. And the conclusion is that this number can be quite large for x absolute near 1. Thus, for x next to 1 or minus 1, the process of evaluating this function is ill-conditioned. So this is like an example of n is equals to 4. This is an example to showcase that well-conditioned and not well-conditioned. Okay, so this is wrapping up. So an overview of error analysis, stability, and other numerical concepts have been considered in this presentation to open us to an horizon to how errors in numerical analysis can be handled. And stability is also checked. Okay, any questions? Thank you. Okay, yeah. So this is the example I explained earlier.
Yeah. Thank you for your presentation. Albeit, I feel that your presentation was a run through, and you assume that everybody knows some concepts here and there, but that's not the case. Okay, let me read one of the questions. So can you help differentiate between rounding and chopping? Please unmute me, please.
Okay.
Please, Israel saying unmute me. Yeah, so as I was saying before the question came up, it appears that you ran through your presentation and you were not patient enough to explain the concepts generally, right? So as a precondition for your grading, do you mind going? Okay, I'm part of the presenter. Okay, I think there's one Israel. Let me make him a co-author. Israel. Okay. Make co-host. Yes. There's Israel. So that's on mute.
Good afternoon, sir.
Yes, good afternoon.
Can you hear me, sir?
I can hear you. You're just joining the class after the presentation is over.
No, I'm sorry, I was working today, that's why. I'm so sorry about that, sir. So
That's not a condition for me to teach you. Either you're working or you're not working. Yeah. So what's the name of the presenter again?
yeah, my name is Nadi Chukwemeka Israel.
No, the person who just presented.
Toby.
What?
Toby.
Oh, okay. Toby, can you go back to the top and teach us instead of presenting a seminar? Thank you.
Okay, can I take it up from here, sir?
You may if you want.
Okay.
From the beginning.
Yeah, good afternoon, class.
Yeah, please, can you put it in slideshow? Because it appears very little.
Just go to slideshow. No, don't add another
slide.
slide. Just go to slideshow.
Up. Home, insert, design, animation, slideshow. Up. Place your cursor up, then left, right. No, right. Up, no. After animation, before review. Yes, just right a bit. No. Yeah, there. So click on that. So from beginning, yeah, so you can start.
Okay, please, Toby, what you do for me, please, just, if I say next slide, just step me to the next slide. So basically, we are talking about error analysis. And in error analysis, it's basically to estimate and minimize errors that are fundamental to error analysis. Now, next slide, please. Next slide. Okay. I will not want to go over the introduction again. I would like to go into the floating point of a number.
So you should start from the beginning, not that we are doing a second presentation for people to understand.
Okay. Like we said, numerical analysis facilitates the difficulties encountered in analytical solution to mathematical problem. When an analytical approach poses difficulty, the numerical approach.
Now, can you explain that first line? You said numerical analysis facilitates the difficulties encountered. How does it facilitate it?
Okay, just to shape our thoughts on this, most problems are solved with analytical method. And in solving with an analytical method, you have to get an exact solution. So numerical
can
analysis.
You speak up a bit?
Can you hear me, sir?
Yeah, just put a little more volume.
Okay, I said most problems we face in mathematics are basically solved with analytical methods. Now, but analytical method cannot solve all the problem. That's why we resorted to numerical method, which is also called approximate method. It helps us give an approximate solution. That is why it is prone to some levels of error, which we are trying to control, in the sense that we have to make sure that the errors are reduced to the barest minimum. So that's why we make use of mostly decimal numbers to calculate for numerical analysis. So
yeah, somebody said, can you be more audible?
let me check. Maybe it's from my iPhone. Okay, is it okay now? Can you hear me now?
Who is this person there? Abdurrahim, Mariam, can you hear him? Can type yes or no. Oh, she can hear you now.
Okay. So, like I said, numerical analysis basically helps us to minimize and optimize errors in a particular solution. So,
No, okay, sorry, sir.
Yeah.
Can you differentiate between numerical analysis and the analytical approach?
Yeah, the analytical approach has to do with getting an exact figure, like in some mathematical problems, like we have some approach that has to do with modeling, which has to do like an abstraction of a real life scenario. So when we use analytical method, it helps us give an estimate, it helps us predict a particular solution, because most analytical method cannot really solve all the problems in mathematics. That's why we have to estimate. So that's why it brings us to numerical analysis. And in numerical analysis, you cannot talk about numerical analysis without talking about error estimation and how you can minimize error or maximize the error. So in essence is when the solution is a bit lower, that the error is being lower. So you say the problem is really minimized. But when you're having a larger error, it shows that it's being maximized.
Okay, sir, we're listening.
Okay, so when we go to floating point of a number. So please, can you take it to that floating point of a number? Okay, no, the first one. Now, looking at the example.
Hello, you have jumped the whole introductory aspect again.
I thought she has done that, sir.
I said she presented.
Okay, okay.
Go back,
okay.
Go back a bit. Okay, you can forward. Okay, forward. Yeah, start from here. No, back. Yeah, continue from here.
Most times we have to use, because of the advent of computers, we have so many applications like MATLAB that we use to estimate problems. So we are also going to be looking at absolute and relative error, which is also a type of error. We have more than that. We have absolute, we have relative, we have percentage error. But for the course of this study, we are looking at just absolute and relative errors. Then we also have Randolph and truncation errors, which we mentioned in our introduction. And we also have well condition and ill condition. Next slide, please. So now, floating point approximation of a number. Like for example, numbers can be represented in different number bases and in standard form. And the standard form is a case like floating point representation. What this is trying to say now is like we have different number systems where numbers are either binary, decimal, octa, hexadecimal. So in this particular example, most floating points are like decimal point approximation, because most of us are familiar with scientific notation, where we use a decimal to write scientific notation of some numbers. Now, given any number, a is not equal to 0. This simply means that this is not applicable when a is equal to 0. Now, as in the peculiarity of this is any number that is different from 0 can be conveniently and successfully represented in this form. Now, from this example that was given below, now we have a is equal to plus or minus, because it could be negative or positive. Then 0, d1, d2, d3. So if dk plus 1, dk plus 2 times 10 raised to the power n, which is the exponential. Where if you are to write this in a more general term, is 1 less than equals to D1 less than equals to 9. Then we also have 0 less than equals to DI less than equals to 9. Now, this is like closed interval where you look at, because we cannot have anything from 9 to the right that will exceed 9 to the right or from 1 to the left. So it's like a closed interval where we know that anything greater than this, it's out of this scope. Had it been there is no inequality sign there, it can be an open interval. Maybe you say maybe 0 less than DI less than 9. So that's an open interval. But for this, it's a closed interval. So we now say for each I equals 2, that means when I equals to 0 will be less than D2 and less than equals to D2 and less than equal to 9. So that's what this is just showing us, how to represent a floating point of a number whenever it is given, so long as it is not 0. Next slide, please.
Just wanted to add that floating point representation shows how a computer stores binary number in its memory. So
yeah. So the next slide. So like I said, floating point approximation. The one we looked at are number basically in base 10, which is as in the one we looked at is decimal. Why this one is like the binary aspect of it, which will still give you the same result. Because if you look at the one in base 2, from the floating point, number can be represented in binary form, in binary number system as this, which is A is equals to plus or minus P times 2 raised to the power M, which is half less than equals to P less than equals to 1. Then you have the same result if you are given an example and we interpolate the figures based on the formula, we'll have the same result. Next slide. So sources of error in numerical computation. Now, blunders are normal human error. We can't rule out error in real life scenario whenever we take a task. Like it says here, this error, also called human error, are caused by human mistake.
Hello. Somebody just said, what does P represent, from Miriam Abdul Salam?
Please take it back. Okay. Based on what we have here, then the P here represents it's called the, I don't know how, it's called the radius. They call it the radius, like the base. Hello, can you hear me?
Yes, I'm listening.
Yeah, the P represent, I'm sorry that I didn't reference the material where I got it from. So the P here represents the radius, which is like the base number that we are doing the floating point to. I don't know if I answer your question, Miriam.
And what is A?
A is the number we are trying to represent. Like I said, A must not be equals to 0, because if it is 0, you cannot represent anything. It's not applicable, because A can either be positive or negative, but not 0.
All right, Madam or Mr. Miriam Absalam, has he answered your question? Yeah, you can continue while we wait for a response. Or either.
Okay, sir. Now, the sources of error. Please take it to the next slide. So, like I said, blunders are peculiar to. Like
yes, thank you. That's what the individual responded.
Okay, sir. So, like I said, blunders are peculiar to human, because human by nature will make errors. Now, modeling errors. These errors arise during the modeling process when scientists ignore affecting factors in the model to specify the problem. Also, this error known as formulation error. Now, what this is trying to say, in mathematical formulation of a real event, a model is simply like a mathematical formulation of a real event. Like you are trying to do an abstract of reality. So definitely there will be some levels of error. Then data uncertainty is if the data you are working on is having some levels of uncertainty, it can also result to error. Then discretization error simply talks about, because in mathematics.
Hello, sir.
Sir?
Yeah, what kind of errors do we have in data uncertainty? Can you give us examples?
Okay, like maybe I'm trying to do like a research, and maybe you have to get data from the net. Based on you are writing a project, you have to get data from the net, or maybe you are also doing like questionnaires, because everybody cannot be objective when they are giving you their feedbacks, because you also, people can give feedbacks subject to themselves. So this can lead to some form of error when you are trying to predict a phenomenon. Thank you, sir. I don't know if I answered your question, sir.
Yes, you attempted. But you know, as a computer science person, we always want to note that when there are uncertainties in our data, there's what we call data cleaning, right? Where we can be able to purge, or a pre-processing. Yeah, we pre-process the data to reduce the amount of error found in the data. So I don't know if this is applicable to your data uncertainty.
I think for the scope of this class, we didn't take cognizance of that.
All right, continue. That was smart.
Okay. In, like I said, discretization error in mathematics. When in mathematics, error simply means when data is in continuous. Like when you have, like we have different ways which we can represent data. We have the analog, which is always continuous, and we have the discrete, which is digital. So most times when you have continuous data like that, continuous problem, you have to change it to discrete value, because this makes it more simplified. It makes it more near to reality, because it makes life very simple. That's what we are trying to pass. Like, let's go back, let's just go through what the author says. He said computer represents a function of continuous variable by a number value. Also, scientists approximate and relate complex solution problem by discreting this result in discretization errors. So next slide, please. So loss of significance and error propagation. When the error level in numerical calculation or computation goes higher, the solution loses its practical significance. Just like what I said initially, like if the error is too large, because we are trying to predict a phenomenon, we are trying to do a research to come up with near to reality solutions. So if the error is higher, then the level of error in that numerical calculation is high, and it can lead to error. So that's why we are even studying this, to know if it is significant or not significant. Like for example, if you are using a numerical method to determine the dosage of a new drug, and the error level in your computation is higher than expectation, the outcome therefore is insignificant and dangerous in application by health experts. For instance,
all right. Now, sorry for cutting you in.
Okay, sir.
Now look at that, what you just read. Say, for example, if you are using a numerical method to determine the dosage of a new drug, and the error level in your computation is higher than expectation, the outcome, therefore, is insignificant. How is this insignificant? Or is it significant? Can you explain that line? The outcome, therefore, is insignificant.
Okay, like for the example, I was trying to explain this. Now, let's say, for instance, a numerical analyst, you are giving.
Sorry, that was a mistake. It's significant. Sorry, it was just, it's my fault. It's significant, not insignificant. So he has a huge impact.
Yes.
So if there's an error, if there's a huge error in the dosage of a drug, it can have a huge impact it can lead to the loss of lives. when the error is large. So is significant, not insignificant. That was my error.
Hello, sir. Should I continue, sir? Hello, can anybody hear me?
Oh, sorry. Yeah, I think I was speaking. I said she should exit the PowerPoint, not exit, just leave the slideshow, correct that insignificant to be significant, save it, then come back to this slide. Escape, escape. Yes. Okay, so go to that slide where there's insignificant. Scroll up. Yeah. So there. Okay, yes. So save. Save is up by that logo. No, just a little. Just go up and press save. Yes, yeah, save. All right, so you can go back to the slide. Slideshow.
You've passed it. I think you've passed it, please.
Yeah, I think this is the place.
Yes, sir.
You may continue, sir.
Yeah, as the error is maximized, the more the result or the solution loses its significance. Thus, to curtail the insignificance in our results, the error margin should be controlled negligibly. So that's saying that like exact solution minus the estimated solution or the numerical solution will give you the error. So we are trying to like make sure that the error is being reduced. That's why we are doing that's why we are even studying error analysis in the first place. Then, like
Sir, can you explain that line again?
I said,
as the error maximizes.
As the error maximizes, the more the result or the solution loses its significance. Thus, that means, like you said, maximize. When the error is high, that means the solution it's because at every point in time, your solution must be close to zero or even exact. So that means the solution loses its significance. Now, to control this insignificance in our results, the error margin should be controlled.
Is it insignificance or significance in error? I don't get it. Probably you should check that. If it's insignificance, then the other one should be insignificant too.
As the error maximizes, the more the result or the solution loses its significance.
Yes.
Thus, to curtail the insignificance in our results, it should be significant. Sorry, sir, it's an error. It should be so. Toby, can you change this one again?
Yeah, I think you should look at that before you send it to the chat group.
Okay, so. Okay, so as the error maximizes, the more the result of the solution loses its significance. Thus, to control the significance in our results, the error margin should be controlled. That is, the error is equal to the exact solution minus the estimated solution or the numerical solution. and must be minimized so close to zero or zero if possible. So
how do we get X?
Now, to X, in most examples that we have seen, the exact solution is always given. And if you want to get X, you just take this error. It will be X is equals to, X is equals to approximated solution plus the error. Because you are moving, you just move the error to the other side to get.
Yeah, somebody is asking, say, I still find that confusing. Why would we be reducing the significance? That's from Mariam Absalam.
I still find that, why would we be reducing the significance? Okay, now, because the error is so large, so we have to, because if you are doing an estimate or a prediction in a research, for instance, you have to ensure that the error is minimized to the barest minimum. Because if the error is so large, that means your estimated value might not even be close to the exact value. Because what we are trying to achieve is to make sure that our estimated value, because since, like I said in the introduction, that most mathematical this cannot just be, because all analytical method cannot solve all the problems in mathematics. That's why at some point we have to maximize. I mean, that's why at some point we have to estimate values. So if the error is so obvious, and your solution will be wrong, because it's going to affect whatsoever model, because don't forget that you're trying to do like an abstract of reality. You're trying to look at, okay, what would be close to the exact solution itself. So I don't know if I answered your question, Miriam.
Yeah, well, we said thanks for your explanation, but I think let me throw a little light into that. Now, I think when we have excess error, which is a deviation from what can be the exact value. Now, if there's a shift forward, like an iteration, when you talk about iteration, just you are going from one step to the other, from the other. So if the iteration is greatly increased, the error is sent to the next iteration or the next computation, which is expanded in that next computation.
Yes, sir. Thank you,
so
sir.
If there's a significance in the error, that means if the error is higher than the actual value, then the next iteration will see a significant deviation from the numerical solution, exact solution that we need to have.
Thank you, sir. Next
yeah,
slide.
So can you also explain what is E, what is X, and what is X star? I think you should have an annotation for it, where E equals this, X equals this, and X star equals this.
So E is basically the error, then X is the actual value, then X asterisk is the estimated value.
Where is that stated in your slide?
Oh, sorry, sir.
We didn't include it, but we will include it when we are sending it to the group.
Can you go back to the just a slide backwards? No. Forward. Okay, yeah, sorry, here. Now no. Where you just left. Here. So you have IE. E equals X minus X star.
Yes.
But in the next slide, we had a cap on that E. Is there a differential?
Yeah, there is.
So what is the E?
So the E that has the cap is absolute error. So because it's a type of error, before we talk about how we can propagate errors, we have to look at types of error. Like I mentioned, we have 3 types, but for the course of this study, we only pick 2, which is the absolute and relative. We still have the percentage error. So the absolute error that has a cap on it is equals to the actual value minus the estimated value.
Okay, that's the modulus.
Yes, sir.
So, but the absolute error value does not have a modulus. according to your
Yes,
formula back.
yes, sir. Yes, sir.
Okay, please continue.
Like you can see no the slide before. I've not talked about the relative. Can you take it back a bit? Okay. Now the relative error of the error is E is defined as the ratio between the absolute error and the absolute value of the exact solution, which is the E cap all over the X bar. So move to the next one. Okay, now in order for us to understand this better, I think an
Excuse
example.
me, sir.
Sir.
Yeah, please, can you go to the next slide before this? Now, you have one E that have like approximation, like almost
Yes,
equal. Then you have one that has like a cap.
yes, sir.
Yeah, what is the difference between this? That's the one that has approximation, a cap, and the one without a cap.
Okay, the difference basically, this one that has a cap is the absolute error. Why this one that has something like an approximation is the relative error. That's the sign used to denote the relative error. Why the one without the cap is just the error itself, sir.
Now, when you are defining it in your updated slide, we want to see a slide that defines the meaning of all these values. The
Okay,
E with cap, the E with approximation, X, the X with an asterisk, and a host of others.
Okay, sir.
Thank you.
Next slide, please. So in this example, we are taking X, which is equal to 3.1, which is like pi that we know in our secondary school, which is like I think 22=7. So I correct 15 decimal places, and the estimated value is also given. So what we are trying to do, we are trying to calculate for the error, the absolute error, and the relative error. Now, like we have from our formula, we have E is equals to the actual value minus the estimated value. So that's what we are doing here to have a result below it. Next slide, please. So for the absolute error too, it's also calculated here. Just plug in your figures based on what you are given to arrive at the solution. The same for the relative error. Next slide, please. So like in our example 2, given that your calculation of Euler's number is equals to 2.178, you obtain 2.178, then find the error, the absolute error, and the relative error. Now,
all right, sir. Please pause at that point. Now, example 2.
Yes, sir.
So given that during your calculation of Euler's number, now can you explain what E is?
Yeah,
and what you obtained? What is the value? What's the name given to 2.18 and 2.178?
So I'm about to get to that, sir, because Euler's number in mathematics is also represented with E. So I know that will be a bit confusing. So, so because is the symbol for Euler's number. So if you look at our calculation now, we're already giving the Euler's number will not take the position of the actual, as in the actual value, while the estimated value is also given as 2.18. So you just slot it in. And another thing I forgot to mention, the absolute value nullifies any negative value, because
that's true.
It nullifies any negative value. So I forgot to mention it. So I'm just trying to call it out again, so that for the course of this example, so that people will understand better. So this next one, Toby, please change it to relative error. There's an error there. It's relative error. The next one that we calculated.
Sorry, what did you say I should change? I didn't get that part.
This is absolute, as in
okay.
It's relative error.
Okay,
yeah, while they are making their correction, I hope all of us are following in the class and we understand what they are taking us gradually. You can type on the chat so that we can be on the same page. All right, thank you for the feedback. All right, thank you, Mr. James Agba, Miriam.
So go back.
All right, thank you.
No. One more step. Okay, it's fine. So like I said, what makes it absolute is because of the value sign, because it means that you must get a positive number because it nullifies the negative value, like I've said. Now, for round off and truncation of errors, we mentioned this in our introduction. This is basically how you round off number to different decimal places. So the truncation error, sometimes called chopping error, occurred when chopping an infinite number and replace it with a finite number by truncated a series.
Hello, sir.
Sir?
Now, the first statement. So computer represents numbers in finite number of digits, and hence some quantities cannot be represented exactly.
Yes, sir.
Is that a truncation or a round?
I didn't get your question, sir.
I say, is that sorry, is that a truncation or a round off? When you are doing this discrete transform.
Yes, sir, it's a truncation, sir, because it has to do with memory capacity of a device differs. Like we know that our calculator is a mini computer. Now, for instance, if I should type 1/3 in a calculator, it gives me, I think, 0.33333. Then it will stop at some point. But if I should do that on the computer, it will continue according to the memory of that device, because memory capacity of device differs, and that leads to difference in the number of digits each device can handle computationally, because some can handle 1 million by 1 million of matrix as a matrix number and even give you the determinant and the inverse of that matrix. So it all depends on the memory of the device, of the computer device. So I don't know if I answered the question.
All right, sir.
Okay, now I won't dwell much here because most of us, like Toby said, most of us know how to round up numbers and what is
Hello,
actually.
sir.
Sir?
Please do not assume.
Okay.
Some of you have learned mathematics for years. So just do us the honor of explaining.
Okay, sir. Like in our example 3, it says approximate the following decimal numbers to 3 digits by using either, I think this side is, we're using chopping and truncation rules. Now we have
I
X1.
think there's something behind that logo.
Yes, I think she needs to
shift it, please.
You need to crop the logo down a bit.
Not now, just do it that later.
Okay.
Do it later.
So we are giving X1 is equals to 1.34579. I think this is up to 5 decimal places. So we are meant to round it up to 3 decimal places, go for truncation and for both rounding off and truncating. So next slide, please. So when you are rounding off, you can see the first one, we have X1 is equals to 1.35 because we know that the last number there is up to 5. So we rounded it to add to the 4, which make it 1.35 to get the 3 decimal places that we are asked to store. So the same thing, but it's just quite different from the chopping, because the chopping, you are not rounding anything. You just stop at exact then 3 decimal places. So these are the results. Next slide.
So
please.
including the decimal, we make it 3. We count from the first digit, then the decimal 2.
Yes, sir.
Okay, sir.
Next slide, please.
Now, somebody is asking, 3 or 2 decimal places?
It's 3, sir.
And that's what I'm asking. That are we going to have that?
We are also counting. We are also
Now, since somebody say this is 2 decimal points. Now, please check the chart so that it won't be as if I'm one reason.
Okay. I
3
think
significant
James,
figures rather.
It's 3 significant. We are counting the points. I just said it.
Please go back to where the example 3 is.
We're also giving reference to that. Go back, sir.
No, I'm not with your slides now.
Oh, sorry, sir. Apologies.
Yeah, here.
So,
nope. Back. Now you said example, approximate the following decimal numbers to 3 digits. Oh, I see.
Yeah, yes, sir.
I think we were confusing it with 3 decimal places.
No.
Apparently, these 3 digits is 3 significant figures.
Significant figures, sir. Yes, sir.
All right, that's okay.
Okay, sir. So next slide, please. So next.
All right, do we understand what is done on this slide by chopping and rounding off? You could say yes or no, so we could move forward quickly. Okay. I think somebody understands.
Okay.
Thank you.
Yeah, still on loss
You can
of
continue.
Okay, still on loss of significance. Now, in a place of relative error, we often use the concept of significant digits that is closely related to relative error. Now, like I mentioned something earlier, we have different, in number system, we have different number base, which we have the binary, the decimal, the octal, the hexadecimal is also there. So like this, I said, I know how to, in their own case, they're using this as radius, but I prefer to call it beta. So let beta be a radius and x is not equals to 0. Like I said, this condition would not hold if x is equals to 0. Now, if the estimated, if AS is an approximation to x, then we say that AX approximates x to significant beta digits. If R is the largest non-negative integer such that x minus xa is equals to this. So what this is saying is, now we are trying to look at the relative error that we have talked about. Don't forget that relative error is absolute error over the, hello, can you hear me, sir? Hello?
Yes, I can.
Anybody hear me?
I can hear you.
I can't hear you.
Oh, really?
Yes.
Ah,
hello?
But I can hear you clearly.
Okay, I can hear you now. I can hear you now, sir. So what we are trying to compare, we are trying to compare the relative error with, we are trying to compare the relative error. That's what we have on the formula. So if we go to...
Hello, sir.
I'm with you, sir.
Okay, please, I think once you are trying to put this in perspective, right? Yeah. Please define, maybe instead of writing x minus xa, the modulus of x, you can just say relative error over another error. So we can be able to relate the formulas.
Okay, sir. So
yeah.
this is basically...
Please note.
Okay, this is basically relative error less than equals to half of the radius, which is the base that you are calculating to, minus r plus 1. This r is always given whenever if you look at the example, r was given. So please, next slide. Now, when radius, I call it beta, is equals to 10, we refer significant 10 digits by signifying the digits. Now, in this example, x is equals to 1 over 3. The approximate number, which is the estimated solution or numerical solution, is equals to 0.33 as 3 significant digits. Now, we already know the formula. So what we are trying to do is just to plug in the figures that we are given. Now, they said R is equals to 3 here. So what they did basically is, we have, it will be 1 over 3 minus 0.33 over 1 over 3. So in order for you to get the 0.01, you multiply through by 3. So you will now have like 1 minus, I think, 0.009, which will give you 0.001. Then, because 1 over 2 is always 0.5. So you will now have, since it's 0.5, so it will not be times, because if you look at the R there is to that beta base. So if you say minus 3 that we are giving, plus 1, you have this minus 10 raised to power 2, minus 10 raised to power 2. So we are just kind of plugging in what we have as the formula to calculate this here. So I don't know if we actually get the explanation. Hello, can anybody hear me?
Yeah, nobody's responding. Did you understand what he just explained? Somebody said, kindly take this again.
Okay.
I don't quite get it.
Okay.
Somebody said that again. It is not clear.
Okay, like I was saying, on this, we already have the formula, which is x minus, that's the actual minus the estimated all over x, and which you have the less than equal to sign 1 over 2 beta. I call it beta because it's quite easy for me than pronouncing radius. So minus r plus 1. Now, if we are to use this formula to solve for what we have been given, we have been given the actual value, we have been given the estimated value, and we have been given r. Now, plugging it into this it will now be 1 over 3 minus 0.33. I don't know if I'm making sense. 0.33 over 0.33. I mean, over 1 over 3. Now, in order for you to do this, you have to multiply both sides by 3. When you multiply both sides by 3, you have, I think, 1 minus 0. Let me. That's how they got this 0.001. Once you do that calculation based on the way I've explained it, you multiply 3 by 3, you have this 0.001. So, and if you have this 0.001, according to the formula, which is 1 over 2 is the same thing as 0.5 times 10 raised to the power minus 2. So that's why they now have to bring it here to be 0.005. So I don't know, Marian, if you got that. Hello, Marian.
Did you get that, please? Well, there's no response yet. I got it. Oh, okay. I got the 0.001. Did not get the 0.005.
The 0.005. Can you hear me, sir?
Yes, sir.
The 0.005 is, let me get my. So the 0.005 is still the same thing as 0.5 times 10 raised to the power minus 2. Are we clear on it?
Okay, do I unmute all of us? Okay, how did we calculate it? Now let me unmute everyone so that when you want to speak, you raise your concern, then you mute yourself back immediately. So let me do that. Oh boy. Sorry. So you can unmute yourself when you have questions.
Please, can you go back to the formula? So my concern is that R, how we are able to, you're able to get it from that computation.
Thank you. The R is already given in the equation. As if you look at the example, the arrow was given to be 3. Can you see it? Toby, please go over around
I
this.
think we are, is it not, are we not calculating for the R?
The arrow is already,
So what am, my
the
question,
arrow. Hello?
yeah, I can hear you. So I think what we are calculating for the significance
Yes,
digit.
the significance of B digits.
So
Yes.
and R is R not their significant digit, or?
No, arrow is part of the equation. You can see that this 1/2. I call this beta, but here they use radius minus arrow plus 1. We are trying to calculate the significance in bit digits.
Okay.
Sorry, can you go back to the next slide?
Okay.
Remember you explained earlier how we arrived at 0.001,
Yeah.
which was 1/3 minus 0.33 over 1/3.
Yeah.
So I understand that part.
Yeah.
The question I was asking was, how did we calculate 0.005?
Okay.
I thought you were using the formula in the previous slide,
Yes.
which will lead to the question of how did we then get R?
Yeah, go to, please, and Toby, take it to the previous slide. Now, if you look at the right-hand side, you have 1/2 beta minus R plus 1. Now, R is already given to be 3. You can see 3 plus 1, you have -2. And you don't forget that we said let beta equals 10. We are doing it in base 10. Now, if 1/2 is already 0.5, which you know, multiply by 10 raised to the power -2 after you have plugged in 3 for R, which is like to the exponent. 3 minus 3 plus 1, which is equals to -2. And
Hello, sir.
Sir?
Yeah, can you, probably using your own writing, could you break this down in the stuff you're going to send in to us?
Yes, I will do
so that, okay, go back to the previous slide. Now, when you see 1/2, is it times or is an exponent?
It's times, sir. 1/2.
Okay, times. Then
1/2.
this beta,
yeah,
is an exponential, Abi. Minus R plus 3 is raised to power.
The beta is the base, sir. Is the base. We are looking at it in base 10. Raised to power R is the exponent. R minus R
Okay,
plus
the
1
exponent.
is the exponent, sir.
Okay, so when you have 0.5, which is half, times 10,
yeah,
minus 3 plus 1.
Yeah.
So -3 plus 1 equals -2.
Yeah.
So you have 0.5 times 10, 10 raised to power -2.
-2, yes, sir.
Is that your explanation?
Yes, sir.
All right, continue.
Please,
I think
slide.
that should be well spelled out when you are
that.
submitting your final copy.
Okay, sir.
Another thing I want to call out real quickly, sir, is saying that does R equals to something is also confusing. It suggests that we are deducing R from the formula, and it was telling us that R is actually given. So I don't know, I think that may also be confusing, because if we put that does R equals to something after we have made a calculation, it almost suggests that we got it from the calculation, but then you said we didn't get it from it.
I think what is actually happening, we are validating that problem is actually a 3 significant digit figure. It's already given that it's 3 significant figure. So we are actually now proving that is a 3 significant figure. It's not like as though we are trying to deduce. That's what I'm getting from.
Can you go to the next slide so that we'll see what is explaining? Okay.
So, can I continue?
You can.
Okay. Like, I want to react to what Miriam said. Like, I kind of get what you said. So maybe when we are sending in our slide, we have to correct this, because this is actually the way the material is, where we got it from. That's the way it was explained. So also, maybe before we submit this, we are also going to explore other materials and see if there are different solutions to this to help shape our thoughts on this. So next slide, please. So stability of numerical computation. Now, the process of evaluating a continuous differential function f at a point x is equal to c is said to be well conditioned. Based on this formula, where c is like the image. So at c is small, otherwise said to be ill conditioned. So we are just trying to prove if a solution is well conditioned or is ill conditioned. Now, with this example, consider the function f of x is equals to root x for all x elements 0 to infinity. Then f of x is, we have to differentiate. When you see f prime of x, we have differentiated x, which is the, you know, the normal formula, which is n raised by n minus 1. That's the formula for that's the formula to differentiate. So which is equals to 1 over 2 root 2 if you differentiate this for all elements of x, for all x elements 0 to infinity. So this interval is called half interval, because you can see the what's it called, the square bracket and the bracket itself. And even a square bracket is known as a closed interval, but this like half interval. If it is bracket, is an open interval. So the condition number of f is f prime over f of x times x, which is equals to 1 over 2 for all elements. Please, next slide. Now, taking the square root of a number, is a well-conditioned process or method. So for this now, for this particular, you are trying to show that even if you use the what's it called, the square root, you arrive at this formula that was given. So, but it's a bit, I won't lie, it's a bit complex to understand how they derive this, because they actually derive it in the material, but I don't really understand it very well. So looking at this example, consider the function. We have f of x is equals to 10 over 1 minus x squared for all elements x, for x elements r. Now, if you differentiate this, you have 20x over 1 minus x squared. So you can differentiate this using quotient rule, where you say let u equals 10 and v equals maybe 1 minus x squared. Then you now plug it into the formula, which is v du dx minus u dv dx all over v squared. Or we can do it differently. We can say, okay, let's
Hello, sir.
I'm with you, sir.
Hello, sir.
Sir.
Yeah, can you hear me?
I can hear you, sir.
Okay, can that be introduced, what you have just said, making u and v, then you do du dv?
Yes, sir.
Can you make that well written in your coming up slide?
Yes, sir.
Yes.
Yes,
sir.
Yeah. So, but there are also other ways you can simplify this without even using the quotient rule. So to differentiate it, you can bring in the 10, then differentiate 1 minus x squared raised to power minus 1, because if you do this now, it will not be 1 minus x squared raised to power minus 1 to the power of 1. Then if you differentiate this, you have 1 minus x all over minus 2, then you have minus 2x. Then if you cross multiply, you still have this 20x over 1 minus x squared all squared. So you can also bring it up in the next, as in the slide we are going to submit, both the quotient rule and the other way to solve it. So And this number can be quite large.
Is your co-presenter noting what you're supposed to put as correction?
Yes, I'm noting it. I'm noting
All
it.
right,
Yes,
thank
I
you.
am.
So, and this number can be quite large, near 1. Thus, for x near 1 or minus 1, the process of evaluating this function is if condition. So I think basically what I can really deduce from here is the closer is a result is better the solution. That's what I can deduce from all this. Next slide, please. This is a bit complex, but I'll try and see how I can explain it to the best of my ability. Now, we said if we have n steps to arrive at a solution using a process or method, and at least one of the steps is or are if condition, the process is unstable. Whenever step is stable, and we can analyze the stability of like you rightly pointed out, sir, you can do a forward integration and a backward integration just to check the two values. So where you have like an initial value and the final value. So if and it also has complex this info, you can read further on that. So there they said let n equals 4 and x is equals to s naught, which is like the initial guess. Now x1 is equals to x naught plus 1, x2 is equals to root x, x3 is equals to root x naught, and x4 is equals to x2 minus x3. Now, like I said, it's like when you are mostly when you are like doing integration, like backward and forward integration. So I just had to bring in this thing just to, as in to a large extent, show that okay, what we are trying to achieve here is if the condition is actually stable or it's not stable, which the explanation is. So I beg to do more research on this. Thank you. Next. So in conclusion, an overview of error analysis, stability, and other numerical concepts have been considered in this presentation to open our horizon to how errors in numerical analysis can be handled, how stable a process can be checked. So personally, I will summarize it like in mathematical modeling of a real life phenomenon. If numerical analysis will be used to solve a mathematical formulation which is useful for prediction of future events, the modeling would be based on existing data, which when solved can be used to predict either weather prediction, financial analysis, just like we have the applications of numerical analysis. Thank you, sir.
Wow, thank you for your presentation. Well, I want to say that the first presenter ran us through the presentation, and he was presenting like a seminar defense. But as I've said earlier on, this should be a form of discussion, and of course, you should also make everybody get at least 70% of what you need to present. And I feel that the other presenters we have done +1 for very enjoyable. All right, I can see some good comments. It's a nice one. There's a clap for you. All right, so well done. Okay, let me open the grade sheets. All right. Quickly, please just unmute yourself so that I call your name. You respond if you're absent. coming. Indeed.
Present, sir.
Okay, so once you just answer, you can just mute yourself. All right. Akin Rolabu.
Present, sir. Akinrola Bulalade.
Okay. Ngbemena.
Present, sir.
Ezekiel Tobi. Elegbede Bankole.
Present, sir.
Then there's one Samuel Chika Mbegbu. Sorry. Is that individual present? All right. Abdurrahim Miriam. Agba James.
Present, sir.
Namdi Chukwuemeka.
Present, sir.
Usia Gusonte Ebenezer.
Present, sir.
Showton Cindy.
Present, sir.
Akinwande Oluwatobiloba.
Present, sir.
Okay, there's an Oluwasusi Victor.
Present, sir.
Okay. Lawal Farouk. Lawal Farouk. Oladipupo Oluwade something.
Present,
Jeremiah.
sir. Present, sir. I'm present.
Okay. Muslimuddin.
Present, sir. Present, sir.
You have been dodging classes since.
Sir.
Abdul Salam Miriam.
Present, sir.
Fakorede Olumide. Fakorede. Why is he absent? Okay, so he joined earlier. Obaji Michael.
Present, sir. Present.
Uluka Prince. Jebutu.
Present, sir.
Moshood Aliu. All right. Have I missed any name? All right. Who are the presenters for today? Your name?
Sir, I am present, sir. Sorry, it's Samuel. You called my name earlier.
Samuel who?
Mbegbu.
Samuel. Where is that one? I can't see the name. I'm coming.
Samuel
Let me look for
Mbegbu, sir.
Samuel. I'm coming. Let me look for it. Is there any other name that is called?
Samuel Chikambi.
Okay, Samuel Chika. Okay, I think I've seen that one.
Sir.
Yeah, who is that?
Muslim Abdulrahman, sir. Sir, last week, during no, sir, so last week, during the class last week, I mistakenly slept off. So I woke up by 3 and I was only able to meet your class. So I wasn't able to make the presentation last week.
You're not able to?
Last week, I slept until 3. So I slept off. Like I wasn't able to meet the presentation class, but I was able to meet your class. So I was in your class from 3 to 5 until you finished the class by 5 last week, Saturday, sir. So I wasn't able to.
5. When did I have another class by 3 to 5. So how come I'm not in class?
Last week when you left also because you said that there's a Nigerian match or something like that.
Is this a master's class?
No, sir.
I finished this class by 3.
Okay, that was the class that I met. Sorry. I mistakenly attended that class because like I slept until 3. So when I logged into the class, I thought it was our class going on. So
how did you get the link to that class?
It was the same link that was on the group. But the same link. So I'm very sorry, sir. I just woke up.
That's strange. How did that happen?
I didn't. Thing is, when I logged in and I saw that the class was on, I found it somehow strange, but I thought that maybe the presentation took from 1 to 3, then your class started from 3 to 5. Because I remember that.
Oh, that was software engineering. This numerical analysis.
I was also a little bit confused somehow.
Then I don't know how you guys are using the same link for that. Maybe I have to correct it then.
So please, sir.
I'll create another link for the master's student.
So please, sir.
All right. Who are those who presented today?
Sir. I'm here, sir.
Your name. I'm on attendance. I'm not on the.
Akinwande Oluwatobiloba and.
I'm coming. Let me look for Akinwande. The names will just disappear. Okay, Akinwande.
Yes.
Okay, so let me go back to the chat group. So what is their grade? Let me see. I think I've marked that present now. Okay. Yeah, he's sending direct message to who? Okay. So is that we have only 2 respondents? Oh, sorry. That's a lot. Whoa. 10, 8, 9. So on the average, they have scored you 9. So what's the name of the first presenter?
Akinwande Oluwatobiloba.
Okay, so you have 9. Who is the second fellow?
Nandi Chukwemeka Israel.
Nandi Chukwemeka. Yeah, so I think the presentation is getting a bit better for you guys to score 9. Well, that's interesting. So we expect that you have problem space with the solution presented to the chat group on Wednesday latest. Yeah, so I saw the solution presented by the former group. Yeah, and I feel that wasn't legible enough and there were too few. So do you want me to grade you based on that, or you want to do something better? Mr. Fakorede
I will
and
do
Mr.
something
Obaji.
better, sir. I will do something better, sir, before Wednesday.
It's something better, sir.
Okay, so I'll hold on with your grade.
Okay, sir.
So you had 8 last
We'll do
week. They had
Yes,
9.
sir.
So we hope that when you turn in your own,
Yes, sir.
that could unsub the grade and make it even. And also those who have scored 9, I hope you also do something better. Do you have an understanding? Yeah, so gentlemen and ladies, you have the YouTube channel, so you could go back to watch. I think there's a lot of noise here. Okay, you could go back to watch the YouTube on the YouTube channel. So you have it there, so you could copy it and send it to yourselves. Let me see.
Sir, sorry, this is Olumide Fakorede. For the attendance, I think you marked me absent. I was trying to speak up, but you did not hear me.
Okay, let me see. What's the surname?
Fakorede.
Yeah, you score 0 now. Why?
That's why I think I did not
You are
hear
just
you
joining
mention.
the class.
No, sir, I was in the class from the beginning.
Okay, corrected that.
Okay, sir. Thank you very much, sir.
Yeah, who is this Moshood Ali? Has he dropped the program? And Uluka Prince. Okay. So next group, we meet. We hope that your presentation will be cool next week. So wish you the best. Be pleasant. When are we playing football? Is it today or tomorrow? Hello?
Tomorrow.
What time?
I'm going to play